Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be taking a quick look at rates of decay. So what we're really doing here is applying kinetics to nuclear reactions. So one of the first things that's very important about nuclear reactions is almost every one of our radioactive decays can be treated as a first order reaction because we always start with the nuclei and we generate some sort of daughter product, so some lighter nuclei usually, and then we produce some sort of radiation event. So let's go ahead and take a look at our major categories. Alpha radiation is going to be first order in whatever we started with, though we do generate two products, a lighter atom, so our daughter product, and in this case, a helium atom. Beta radiation, I'm going to go ahead and take, again, this thorium, and I'm going to generate an electron and another atom. So again, mass doesn't change, but honestly, that doesn't matter. It's still a first order reaction. Gamma radiation, all I'm doing here is releasing light, so it's first order. Positron decay, okay, this time I'm releasing a positron, but it doesn't matter, it's first order. So all of these reactions we've looked at so far are all first order. The only one that isn't is electron capture, where I start with a nuclei, I gain an electron, and then I generate a new nuclei. But it is worth noting that even in this case, that electron often is a core electron. So you can still treat it as first order in beryllium because the electron doesn't have to travel any distance and its concentration won't come into play. So in all 5 of these events, we can look at our radiation events as first order. And that really is nice because since I use first order reactions, this means I can develop a modified first order rate law specially made just for nuclear reactions. So the big thing we're going to note here is that I'm going to switch out a rate of reaction for what's called a rate of decay. And nicely enough, we don't even have to worry about stoichiometry here. The rate of decay is often sometimes known as an activity, so it's given the symbol of A. And this will be simply related to the number of radioactive elements. So again, big note here is instead of looking at concentration of a radioactive element, we're going to simply be looking at their number. So this is often used as a count of the number of radioactive atoms, though it can also be used to treat a mass. Then, again, we have our rate of decay. So this will be the number of atoms or mass that will decay per unit time. And then here our lambda is called our decay constant. So this will just be a good old first order unit rate constant. So only has units of per time, often per year, but occasionally per second, per decade, or per millennia. And really, this is going to be our nuclear rate constant. This is our activity or rate of reaction, and we're switching out concentration for a simple number of atoms. So what we can do is, using this, help establish an integrative radioactive decay law, where now we have a natural log of the number of radioactive atoms at time t, and the radioactive atoms at time 0. And t simply will relate the amount of time that's passed. Do make sure that your time and your rate share the same units, and you'll be golden. However, we frequently don't use the integrated rate law in this form. Most of the time, we're much more interested on how the amount of time passed relates to the ratio of the change in constant in the number of radioactive atoms. So you can do that by combining our natural log functions on the left-hand side of the equation. So we have the natural log of the ratio of the amount of radioactive atoms at time t versus initial versus the amount of time that's passed. Now, one of the most important time events to keep in mind is going to be what's called the half-life. This is the same half-life that we've seen before. And the nice part is, since we have a first order reaction with no stoichiometry, I can simply treat the half-life as the natural log of 2 over the decay constant, which again, think rate constant. And it is worth noting that we can evaluate the stability of a whole bunch of our semi-stable atoms based on their half-lives. If we have a nice long half-life, it will be a slow reaction. So go ahead and think about something like potassium 40, which lasts on the order of billions of years. On the other hand, we have things like polonium, which has a half-life of less than 10 of about 10 to the negative 4 seconds. Once we get down to these very short time periods, this means that the rate of reaction goes very quickly, and we can consider that element highly unstable. And so we can use these ideas of the half-life being related to stability to go ahead and take a look at our radiation series, or uranium series. So we saw uranium go ahead and go from uranium-238 down to lead-206. I went ahead and combined some of the rapid beta events with some of the corresponding reactions, and I combined the lead-214 to 206 series together for convenience. Now, what you'll notice is the initial decay of uranium is very slow. It has a half-life on the order of about 5 billion years. So in other words, very little uranium has probably decayed, just period. However, we notice that the subsequent reactions go anywhere from 24 days to about 250,000 years, 75,000 years, about 1,000 years, down to like 3 days, down to 3 days or 3 minutes. And it is worth noting that you'll note that radium, again, which was originally used as dye in a lot of scientific experiments, gave Marie Curie her reputation, has a half-life of about 1.6 thousand years. This means that it is present in high enough concentrations it can be observed, but it has a low enough half-life that it will quickly react at a rate that you can go ahead and observe. And one of the big things to note is, just like any sort of reaction series, the general rate of reaction will be controlled by the slowest step. In this case, the slowest step is by far the uranium decay. It is over 19,000 times slower than the next slowest step, which is the decay of uranium-234. This means that I can go ahead in any sort of uranium decay reactions, treat this first step as the rate limiting step, and assume that we'll rapidly go from thorium to lead, because on a grand scale, that's actually quite true. And so as a result, if I know the amount of lead uranium-238 in a system, and I know the amount of lead-206, I can have an idea of about how much 206 was formed via this pathway. And using that ratio, I can say, okay, I formed this much lead, how much uranium ended up decaying, and use that corresponding with the half-life to figure out the reaction. However, one of the things that is worth noting, lead does occur naturally. And so this is often corrected by using the amount of lead of other isotopes and assuming that they're generated in fairly even in the abundance and the same ratios as is present in non-uranium ores, which works fairly well. So one of the big things is we know that all of these reactions are first order. So we can go ahead and use our overall rate of reaction based on the limiting step. And then I can go ahead and figure out, using the half-life of the rate limiting step, I can relate that to the rate of the reaction, again, using my rate constant. Then, as long as I know the initial amount or concentration of a radioactive species, if I measure the concentration at a given time, I can figure out how much time has passed. And this is really what constitutes radioactive dating. First, establishing the ratio change, getting the rate constant from the half-life, and then solving for the amount of time that's passed. So one of the big things is that because these rates of decay are fairly constant, I can go ahead and combine these equations to figure out exactly how old a sample is. So let's go ahead and use some real data. So assuming we found a rock from the Rockies that is known to be rich in uranium ore, I find that the amount of uranium in a given amount of ore of U-238 is about 13 grams, and that I've got about 2.55 grams of lead. Assuming I've already removed the amount of lead that would be present due to natural abundance, and that all of this lead came from the uranium cascade, what would be the age of this rock? So the first thing I need to do is go ahead and convert from the amount of lead and uranium I have to just figure out the initial amount of uranium. So uranium at time 0. So this will be the amount of uranium that I currently have, plus the amount of uranium I lost. Now, the big trick here is that I've got masses of both. So I need to go ahead and use good old-fashioned stoichiometry, knowing I started with about 2.55 grams of lead, turn that to moles of lead, and know that every 1 mole of lead was produced from 1 mole of uranium, which has a slightly different molecular weight. So it turns out to produce that 2.5 grams of lead, I lost about 3 grams of uranium. So combining these numbers, turns out our original mass was just under 16 grams of uranium. Now, knowing that I have 13 grams and I started with about 16 grams, what's going to be the age of the rock? So for that, I'm going to need this equation. Now, I've got my ratio. I need to solve for time. But first, I need my decay. So my rate of decay can be determined from the half-life. Again, just using natural log of 2 over a half-life. Do note that my half-life is going to be in years, as denoted by this A. So it turns out that the rate of decay for uranium is about 1.5 times 10 to the negative 10th per year. Yeah, that's a pretty small number. But I can then use this to solve for the amount of time that's passed. Plugging in all my numbers, it turns out that the Rockies are about 1.4 billion years old. And that's pretty spot on. So it turns out you can do very similar techniques with almost all of the radiation dating techniques. As long as you're able to figure out what the initial amount was, you can go ahead and figure out how long the sample has been. As well as, much more practically, we can use these idea of half-lives and rate of decays to figure out how long a person who's had a radiation therapy or a radioactive dye tracer will have to deal with levels of radiation. So until next time, take care. Next time, it's going to be fusion and fission. Until then,